Hi viewers, I wholeheartedly welcome you to this particular session wherein I am going to discuss a very important topic of inorganic chemistry, namely boranes. Boranes are the binary compounds of boron with hydrogen, and in this particular SLO we are going to focus on the classification of boranes, the preparation of diborane and the structure of diborane with more emphasis on electron deficient nature of diborane. As I told you, boranes are binary compounds of boron and hydrogen alone. So the general formula of boranes can be BXHY. Boranes are basically classified into two types. They are, first type is BN HN plus 4. The other one is BN HN plus 6. The example for the first category will be B2H6, in short is also called as diborane, B4H8 tetraborane with 8 hydrogens, and if N is equal to 6, this becomes B6H10. This is called hexaborane 10. Now the examples for the other category include B4H10. The name of this borane is tetraborane 10. If I put N is equal to 6 in the above formula, then I am going to get B6H12. This is hexaborane 12. So in this way, boranes are binary compounds of boron and hydrogen with general formula BXHY are classified into two types, namely BnHn plus 4 and BnHn plus 6. So we are going to focus on diborane. We are going to see the preparation of diborane and the structure of diborane in detail. Diborane can be prepared by using several methods. One of them will be the reduction of boron trifluoride. So boron trifluoride, namely BF3, on reduction with lithium hydride gives diborane at elevated temperatures. So we need to perform this particular reaction at elevated temperatures, and the byproduct here is lithium fluoride. Now try to balance this particular reaction. You need to take 2 moles of BF3 and we need to have 6 moles of lithium hydride such that we get 6 moles of lithium fluoride as a byproduct. So this is the first method of preparation of diborane. Here diborane is obtained by the reaction of boron trifluoride with lithium hydride. Now the second method is a very important method where diborane is prepared by the action of boron trichloride this time, namely BCl3, with a very strong reducing agent, namely lithium aluminium hydride LiAlH4. Now here the byproducts include lithium chloride LiCl and aluminium trichloride, namely AlCl3. Now we need to balance this reaction also. So how do you balance this particular reaction? To balance this reaction, we need to take 4 moles of BCl3 and we need to take 3 moles of lithium aluminium hydride, and you are going to get 2 moles of diborane, 3 moles of LiCl and 3 moles of AlCl3. So now let us focus on the third method, which is the best method for the preparation of diborane. In this particular method, diborane is prepared by the silent electric discharge of boron trifluoride gas with hydrogen. So I am taking boron trifluoride gas and I am treating it with hydrogen in a discharge tube. On silent electric discharge, I am going to get diborane B2H6, and here the byproduct is HF. So I am going to take 2 moles of BF3 and 6 moles of hydrogen, and I am going to get 6HF as a byproduct here. That's all. When we focus on the structure of diborane, the formula of diborane is B2H6, which is very similar to that of ethane, namely C2H6. Therefore, we presume that the diborane may be having a structure which is equivalent to that of ethane, namely C2H6. However, the number of valence electrons do not support this particular presumption. In diborane, we have only 12 valence electrons. Now let's go to the board to discuss in detail the structure of diborane. Now when we focus on the structure of diborane, I told you diborane is having 12 valence electrons. So B2H6, 3 each from 2 borons, namely 6, plus 6 electrons from hydrogen. So totally 12 valence electrons are there. Therefore it can form 6 bonds. Ethane, on the other hand, is having 14 valence electrons. 4 from each carbon, therefore 8 valence electrons, and 6 from 6 hydrogens, totally 14 valence electrons. Therefore, it can form 7 bonds. Hence, the structure of ethane is conveniently written in this fashion, like this. So, 3 hydrogens here, 3 hydrogens on the other carbon. So, totally it is a ditetrahedron structure. Similar structure to diborane is ruled out. Why? Because we have only 12 valence electrons. So these 12 valence electrons, when they are converted into bonds, now we don't have a bond left for B and B. This is the scenario. So we don't have electrons for bonding between the 2 boron atoms. Therefore, a similar structure as that of ethane is ruled out. When we further explore the structure of diborane by experimental methods, namely XRD studies and NMR spectroscopic studies, we came to know that there are 2 types of hydrogens in diborane. So, the overall structure of diborane was found to be a 3-dimensional structure of this kind. It is having 2 BH2 units like this, and we have 2 bridged hydrogens in this manner. So this is the overall structure of diborane, and we have different bond angles. Namely, this bond angle is 97 degrees, whereas this bond angle is 122 degrees. So there are 2 types of hydrogens in diborane. The 4 hydrogens which are at the terminals are called as terminal hydrogens, and these 2 hydrogens which are bridged between the 2 boron atoms, they are called as bridged hydrogens. Now, how do you explain the so-called experimental structure of diborane by using orbitals theory or valence bond theory? That is another important point. Now, even the BH bond lengths are different. For example, this BH bond length is 131 picometers, whereas this BH bond length is 118 picometers. So now we need to explain this structure of diborane using our orbital theory. So in diborane, the central atom is boron. So the atomic number of boron is 5 and its electronic configuration is 1s2, 2s2, 2p1. If we write the box representation, it is 2s2 electrons like this, and 2px1, 2py0, 2pz0. But in the excited state, one electron gets promoted from 2s orbital to 2py orbital. As a result, I am going to get the electronic configuration in the excited state as 2s1, 2p2, like this. This is the scenario in the excited state. Now, on each boron, one 2s orbital and 3 2p orbitals will undergo sp3 hybridization. Very, very important. So on each boron, one 2s orbital and 3 2p orbitals, totally 4 orbitals are undergoing sp3 hybridization. So on each boron, we are getting 4 identical sp3 hybrid orbitals like this. So these are the 4 identical sp3 hybrid orbitals on each boron, sp3, sp3, sp3. And out of these 4 orbitals, 3 sp3 hybrid orbitals are having 1 electron each like this. And 1 sp3 hybrid orbital is empty. Now the same scenario is observed on the other boron also. So on the other boron also we have 4 sp3 hybrid orbitals formed like this. These are 4 sp3 hybrid orbitals, sp3 hybrid orbitals, and 3 of them are having 1 electron each like this, and 1 is empty. Now what are the other orbitals we have? The other orbitals we have are the hydrogen atom 1s orbitals, because hydrogen is having atomic number 1, therefore its electronic configuration is 1s1, therefore it is having half-filled 1s orbital like this. Now this half-filled 1s orbital of hydrogen overlaps with half-filled sp3 hybrid orbitals of boron to form the terminal BH bonds as shown here. So 1s orbital of hydrogen, 1s orbital of hydrogen, 1s orbital of hydrogen, and 1s orbital of hydrogen. So in this way, 4 terminal BH bonds are formed. Now totally how many hydrogens are there in diborane? In diborane, the molecular formula is B2H6, therefore there are totally 6 hydrogens, and we have utilized already 4 hydrogen atoms. Now 2 more hydrogens are left. Now the 1s orbital of hydrogen overlaps with half-filled sp3 hybrid orbital of one boron and empty sp3 hybrid orbital of another boron, forming a BHB bond, and this is called as a 3-centered 2-electron bond. It is also called as banana bond. So we have 2 such type of banana bonds in diborane. So let us focus on the 1s orbital of hydrogen overlapping with empty orbital of one boron and half-filled sp3 hybrid orbital of another boron, forming another BHB bond. So this is the explanation offered by orbital theory for the experimentally observed structure of diborane. So towards the end, we may write the structure of diborane as boron, boron, and then 4 terminal hydrogens like this, and we have 2 banana bonds which are represented in this fashion, and out of these 2 banana bonds, very important factor is that we have only 2 electrons, 1 electron from boron, 1 electron from hydrogen, as indicated in this diagram. So we have to draw this structure also in the final exam to get good marks.